All right. So, in the last class we were reviewing some basics of sampling. So, let us quickly recap what we did in the last class. So, let us say we had a continuous time signal x of t and we sample it at a uniform rate every t seconds, then we get a discrete time signal where time is quantized, but amplitude is continuous, and we were trying to relate the spectrum of the continuous time signal to the spectrum of the discrete time signal. Okay. And we said that if the continuous time signal had a spectrum x of f and we denote the discrete time Fourier transform of the sequence x of k t by x of e to the j omega, which is sigma over all k x of k t e to the minus j omega k. All right. And to remind ourselves that this signal here corresponds to continuous time, I will label this chap with a subscript x c of f, and to remind ourselves that this is a discrete time spectrum, I will call that x d of e to the j omega, right. And yesterday we saw that x d of e to the j omega can be simply obtained by forming the sum over all k of x c of f minus k by t times 1 over t, right, and then replacing we replace 2 pi f times t with omega, all right, and therefore, x d of e to the j omega is simply sigma over all k x c of omega by t times 2 pi, right, minus k by t, all right. And instead of writing 1 by t all over the place, if I denote 1 by t by the symbol f s, stands for sampling frequency, then x d of e to the j omega can be written as 1 over t times sigma over all k x c of f s by 2 pi times omega minus 2 pi k. All right. And one must remember that x d is periodic with two pi, all right, and when a continuous time sinusoid of a frequency f 1 is sampled at a rate f s, what kind of sinusoid will that result in the discrete time domain? Let us say you had a continuous time sine wave with a frequency f 1, when you sample it at a rate f s, it will become a discrete time signal, correct. What do you think the frequency of that discrete time signal would be? It will be f 1 by f s times 2 pi. Is this clear? Okay. So, in particular DC will transform to DC, I am just putting that down here again. DC will transform to DC, Fs by 4 will transform to Fs corresponds to 2 pi. So, Fs by 4 will correspond to 2 pi by 4, which is pi by 2, Fs by 2 will correspond to pi, and Fs corresponds to 2 pi. Okay. And a very easy way of drawing the spectrum is to do the following. If the continuous time signal had this spectrum, how do you draw the discrete time spectrum? The first thing would be to make copies of this, right, with a period. Let us say this bandwidth was b hertz. Okay. I will make copies of this at Fs. So, let me just do that here. Right. The next step is to multiply all of this with 1 over t and then replace, scale the x axis, where b becomes b by Fs times 2 pi, all right, and Fs becomes 2 pi, 2 Fs becomes 4 pi, and so on. And as we all agreed yesterday, the discrete time spectrum is periodic with a period 2 pi. So, it does not really matter which particular period you choose, right, and it is common to choose the range from minus pi to 2 pi. Is that clear? Now, a couple of things I would like to bring to your attention. The first thing is that if you had a continuous time signal at a frequency f1, it will transform to, as we discussed just now, 2 pi times f1 plus f1 by Fs. Now, what if you had a continuous time signal which was f1 plus Fs? The frequency of the sinusoid was f1 plus Fs. If you sample it at Fs, what do you think it will look like in the discrete time domain?
Same, sir.
Please notice that it, I mean, you would say it is 2 pi times f1 plus Fs by Fs, right, which is 2 pi into f1 by Fs plus 2 pi, but we know that the discrete time spectrum is periodic, correct. So, everything is modulo 2 pi. Okay. So, you can remove the 2 pi. So, what this is telling you is that a frequency f1 and a frequency f1 plus Fs, when sampled, will look like the same frequency in the discrete time domain. This is nothing but aliasing, and this makes sense also, right, because from the Nyquist theorem we know that if the input frequency is greater than Fs by 2, then it will result in aliasing. Okay, this is an illustration of that. It just says that if you have a frequency f1 plus fs, it will look after sampling just like f1. Is that clear? Now, by the same token, f1 plus k times fs after sampling will also look like 2 pi f1 by fs. I mean, this is assuming that f1 lies between 0 and fs by 2. Okay. So, in other words, when you sample a continuous time signal, there are many frequencies that can masquerade like the I mean there are many signals which kind of map down to the same discrete time sinusoid. So, if you are not careful before sampling, then you can be thoroughly mistaken as to what the continuous time signal is. Please note that the idea in the whole the idea behind sampling is to be able to eventually reconstruct the input signal in some fashion, correct. If you have lost information while sampling or you made errors during sampling, it is very difficult to recover. So, which is why, as we were discussing yesterday, we said that while it is true that the desired signal may be of only a small bandwidth, there is always accompanying noise whose bandwidth could be much wider than the bandwidth of the desired signal. Now, we should not get into the mistaken notion that the desired signal has only got a bandwidth b, so I will only sample at 2b. Okay. So, if we do not do anything, then noise components which are much broader band than 2b, as we just saw, will all alias to in band, okay, thereby degrading the in band signal to noise ratio. So, the way around this problem is to not sample the signal directly, but to put a filter called the anti-alias filter, which makes sure that the bandwidth of the signal is what you think it should be, and then the output of the anti-alias filter is sampled, and thanks to the anti-alias filter you know that the signal bandwidth does not exceed b, which means that I am safe if I sample at 2b, right. This is what you have seen in the communication textbooks, all right. And when we are dealing with mathematical abstraction, it is often very convenient to assume brick wall type filters and so on. So, in your communication class it is very likely that you have seen a block diagram where you have an ideal low pass filter whose bandwidth is b. In other words, it allows everything to pass through below b and cuts off everything beyond a bandwidth b, and by now you should know that this is not possible. Any practical filter that you build with a finite order will only have the only thing you can do is make the transition band narrower and narrower. You cannot make the pass band absolutely flat, you cannot make the stop band attenuation infinite, which is what one would tend to believe. If you if you saw the ideal block diagram of a anti-alias filter, it would look like a brick wall filter with one ideal anti-alias filter. You would expect the frequency response to look like this, where this is 0, this is 1, this is the bandwidth b, right. A practical filter can only approximate this in some sense. So, you will find that a, the pass band is not as flat as you would want, the transition band is not as sharp as you would want, and the stop band attenuation is not as large as you would want. Okay. Now, given this information, can you comment on A? Are there any considerations you think for the sampling rate? In other words, we know that if a signal has a bandwidth B, we need to at least sample at 2B, and we also know that we must put an anti-alias filter. Now, the question I am asking you is, do you think it makes sense to sample at not at 2B, but at 4B? 2B satisfies the Nyquist criterion, 4B satisfies the Nyquist criterion, 40B satisfies the Nyquist criterion. So, it is natural to wonder whether should I just sample at Nyquist. After all, Nyquist is telling me that if I sample it at least the twice the bandwidth, I will be able to reconstruct, no problem. The question is, should I sample only at 2B? Is 2B good enough, or am I doing better if I sample at 4B, or am I doing even better if I sample at 8B? Do you have any comments? Is there anything we gain? It seems like it is more difficult to sample at a higher rate, right? So, the question is, do we gain anything at all in this bargain?
Stop band if attenuation is not finite, then to make the rate much more, then you will have less aliasing.
Okay, very good. So, the suggestion is the following, right. So, let me draw spectrum. Let us say this is 0, I will only draw the positive half, this is F. I will draw the characteristic of the anti-alias filter in red here. And let me draw this on a log scale. So, this is log magnitude of the anti-alias filter response, and because the filter has got a finite order, as you move away from the band edge, right, this frequency below B is the so called pass band of the filter, the portion beyond B is the stop band of the filter. Because the filter is a practical one, it is a real one, the order is finite, which means that you can never have infinite stop band rejection over a band of frequencies. You can have it at one frequency or two frequencies, but not over a band. And if you have an all pole filter, an all pole filter is one where the numerator is 1, right, H of s is a form 1 by d of s. Okay. So, if you have an nth order filter for large frequencies, how do you think the attenuation will go? For frequencies far away from the band edge, it must go down as 1 by omega to the power n, which is 20 n dB per decade, correct. So, if this is a linear scale on the x axis and a log scale on the y axis, it will look like this. If I plot a log plot, it will be a straight line with a slope of minus 20 n dB per decade, right. Now, let us consider two situations. One, the signal frequency is, the desired signal is here, okay. Let us consider two sampling rates, one where the sampling rate is Fs, the other one where the sampling rate is, let me call this Fs1, and the other one where the sampling rate is Fs2, all right. All right. So, now can you comment on the consequences of these choices, FS1 versus FS2, what do you think becomes more simplified if you choose FS2 versus FS1?
Signal bandwidth, the noise component will be the higher frequency component, the aliasing of the eye.
Okay. So, first thing we need to understand is that if there was no noise at all, we would not have to worry about the anti-alias filter, right, because the sampling rate evidently is much higher than twice the bandwidth. The problem or the reason why we need to have an anti-alias filter in the first place is to filter off noise, right, and where do we want to specifically get rid of noise? What is the job of the anti-alias filter?
Within the bandwidth of the signal.
See, you can't
Outside the
Beyond, outside the required band.
where outside the required band. The question is it important to get rid of noise all outside, I mean completely outside the signal band, or are there specific locations where you really want to get rid of noise? Between? No. Can you be a little more specific? B and Fs of course is good, but
B in the zero.
where do we want to get rid of noise? We want to get rid of noise at all those frequencies which can potentially alias to the in band frequencies, correct, which is the in band frequency 0 to B. So, now we need to figure out which all frequencies will alias to the range 0 to B. Okay. Let us start with 0. Which all frequencies will alias to 0?
FS1.
Obviously,
FS1.
0 will translate to 0. Okay.
FS1.
FS1, FS twice FS1,
3 FS1.
all integer multiples of FS1 will all alias to
0.
okay. So, we need to definitely get rid of noise at FS1. Now, what frequencies will alias to B? FS1
Plus B.
plus B, 2 FS1 plus B and so on. You must remember also that there is minus B. So, what will alias to minus B? Minus B plus FS1, minus B plus 2 FS1 and so on. So, now we know what all frequencies alias to 0, what all frequencies alias to B. So, we know, I mean all the range between also will alias to something between 0 and B. So, FS1 plus B, right, this is FS1 plus B, and FS1 minus B is this range here. So, this is a band of frequencies where signal will alias to minus B to B. You understand? While it is true that it would be great if we had an anti-alias filter which would just cut off everything beyond B, we know that in practice it is not possible. Is that clear? So, the next question is, okay, where do we really want to cut off noise? And we really want to cut off noise at frequencies which can alias down to the range minus B to B, and that will be in the, if we chose FS1 as the sampling rate, it will be FS1 minus B to FS1 plus B, right. Now, if instead we had chosen FS2 as the sampling rate, what do we see? Which all frequencies will now alias to baseband? FS2 minus B to FS2 plus B. All right. Now, can you comment on which of these is a better choice of sampling frequency and why?
FS2 plus minus.
FS2. Why is FS2 a better choice?
Stop band will
Rejecting is
until
easy.
rejecting.
Right. So, we see that if we chose FS2, then the rejection
will be
for a given anti-alias filter, the rejection
will be
of the anti-alias filter
Is high.
will be higher for a higher choice of sampling frequency, right. Okay. So, even though it appears that it is harder work to do to sample at a higher rate, while Nyquist just dictates that twice the bandwidth is enough. We see that choosing a sampling rate which is much higher than what is dictated by Nyquist is advantageous in terms of the design of the anti-alias filter, correct. Now, let us take this argument the other way. If I insisted that I want to sample at Nyquist, in other words my sampling rate is 2B, what do you think the characteristics of the anti-alias filter must be? It has to be
Sharp call.
lot sharper than what we have now. Does it make sense?
Yes.
Okay. So, choice of sampling frequency relative to the Nyquist frequency What is the Nyquist frequency? The Nyquist frequency is the minimum bandwidth minimum sampling rate you require to sample a signal of bandwidth B. So, the Nyquist frequency in this particular example is 2B, right. So, the choice of the sampling frequency related to the Nyquist frequency has implications on the design of the anti-alias filter. So, to compare different sampling rates, it makes sense to only compare it with respect to the Nyquist rate, correct. So, 2B is the minimum sampling rate required to be able to reconstruct a signal with bandwidth B. If you are sampling at a rate over and above 2B, it means that you are, if you are sampling at Nyquist, you are sampling, okay. If you are sampling at a rate higher than Nyquist, you are over sampling, right. So, the ratio Fs by 2B is called the over sampling ratio, or the abbreviated as the OSR. So, we will repeatedly keep using these things this abbreviation later in the course, right. You understand why this definition makes sense. So, now to rephrase all that we have discussed with this new jargon, if my O sampling ratio is high, what does it mean? Is my anti-aliasing filter design easier or more difficult? It is easier, okay. Another thing we need to bear in mind is that it is only in the textbooks that you have an ideal filter. It is only in the textbooks where you have you have a filter with a bandwidth B and the bandwidth is actually B. In practice, whenever you say I am going to have a filter B, you must be prepared to take variations in the bandwidth, because no real system will have a bandwidth which is absolutely fixed. This bandwidth will vary, perhaps because of temperature variation, because of manufacturing tolerances and so on. So, in practice it is never possible to ensure a bandwidth which is exactly what you want, okay. So, a high OSR means that the anti-alias filter need not be very sharp. Why? Because if you want to reject the alias band to a certain level, if you increase the O sampling rate, which O sampling ratio, which is the ratio of the sampling rate to twice the signal bandwidth, then your anti-alias filter must satisfy. In the passband you want your anti-aliasing filter to have a gain of 1, right. In the alias band you want it to have a gain of 0. Of course, we do not ever really expect that gain to be 0, we want it to be some small number, correct. So, if we say we want the gain in the alias band to be at least smaller than, I mean at most some number like this, then the filter design problem becomes a lot simpler, because the filter needs to have a transition band which is doing this, correct. On the other hand, if my oversampling ratio is small, then what happens? I need to have the same rejection in the stop band, okay, and I need to have the same transmission in the pass band. So, this means that my transition band from pass band to stop band must be very sharp, okay, and designing sharp filters is more difficult than designing filters which roll off gently, okay. Without getting into the theory, I mean, well, this seems at least intuitively satisfying, okay. All right. Not only that, can you comment on the effect of variation of this filter corner as you change OSR? In other words, do you think I can tolerate a bigger variation of the band edge, the motivation being that no practical filter will have a band edge which is fixed in frequency, it will vary. The question now is, does it make any difference if I increase the OSR? Can I, in other words, can I tolerate a larger variation of band edge frequency with a higher OSR?
Yes.
Do you understand the question? No. See, we know that the anti-alias filter bandwidth cannot be fixed, there will be some tolerance, it will move, right, and you want to make sure that in spite of this bandwidth moving, the band edge moving, you want to make sure that it rejects the alias band to some degree. Now, the question is, will you be able to tolerate a larger variation of this band edge when the oversampling ratio is small or when the oversampling ratio is large, right. So, it is very straightforward. So, if the oversampling ratio is large, not only is the filter design easier from a point of view of the width of the transition band, okay, it will be a lot more tolerant to variations in the band edge frequency. To see this, imagine what happens if you have Nyquist sampling, the filter must be really sharp, okay. And now if the bandwidth even moves a little bit, right, if the bandwidth reduces, what happens? It will get rid of the alias for sure, but it will also cut off some of the desired signal, right. On the other hand, if the bandwidth increases, then what will you see? Some of that alias band is not properly rejected, okay. So, while it is true that Nyquist sampling is all that is necessary to be able to reconstruct a signal properly, there are some very practical reasons why you would want to actually oversample the input signal. So, I mean, typically you would never have a system where the signal bandwidth is say b hertz and you sample exactly at 2b, right. This will make the job of the filter designer very difficult. Of course, you can say it is not my problem and somebody else's problem, right, but you could, I mean, in the next project you could be that somebody else, you understand. So, it is very common to have a little bit of oversampling, so that the job of the filter designer is made easy. Of course, pushing the sampling rate high is also not a trivial affair, you understand. So, that basically means that your circuits have to work that much faster, right, but system design is a trade off between these possibilities. If you try to make your job easy, somebody else's job becomes a lot more difficult to do. If you want to make that guy's job easy, then your job becomes very difficult to do. So, you sit together, both of you sit together and figure out what works best for both of you.
Sir, whether stability criteria will also come into the picture.
Meaning
The transition band what we are talking about.
Right.
Suppose we are having the low sampling rate.
correct,
Then transition has
will
to
be very
sir.
sharp, correct.
So whether any chance of that stability criteria.
Well, it is true that if you have, the comment he made was that if your oversampling ratio is very small, then the filter has to be extremely sharp, and the comment he made was that if the filter has to be extremely sharp, then that response must only be possible by poles whose quality factors are extremely high, only then you can get a sharp roll off. Okay. And yes, that is indeed a challenge. Once you have very high Q poles, it turns out that the sensitivity of the circuit to component variations also becomes high, as you might have seen in perhaps your digital filter design class. The same thing also holds for analog filters. Whenever you want to make something very rapidly in the frequency domain, sensitivity to component tolerances, noise, etc., at those frequencies becomes large, and therefore you would like to try and avoid very sharp filters if possible. Okay. All right. Yes.
Second, this bandwidth criteria, whatever we are talking tolerance, how much percentage we will take? Means suppose we are having the say for example our audio signal 20 kilohertz. Suppose we are talking, how much we can go for the sampling rate?
Oh well, the question he asked was, if you have a signal with a certain bandwidth, how will you choose your oversampling ratio, right? So, will you choose a very small number or will you choose a very large number? This is very situation specific. When you are dealing with low signal bandwidths, for example audio, it is very easy to sample at a higher rate given today's technology constraints, right. For example, a 24 kilohertz audio signal, a common sampling rate to use is say 6 megahertz, 6.144 megahertz. So, if let me just take an example since he has brought it up. So, the signal bandwidth is 24 kilohertz. The Nyquist bandwidth is what? Nyquist rate is 48 kilohertz, and if the sampling rate is 6.144 megahertz, what is the oversampling ratio?
Around 120.
It is?
Around 120.
It is 128. Okay. All right, and this turns out that is a fairly common thing to do. And as you can see, the alias requirements, given that the oversampling ratio is 128, the anti-alias filter needs to have, it can be actually very gentle, because it needs to pass, it needs to have a flat gain only up to 24 kilohertz, and it needs to have high attenuation only at 6 point something megahertz, right. So, very often a simple RC or a combination of RC passive RC filters is all that is needed. Okay. And one might also ask, given that I am doing all this extra work, I need to sample only at 48 kilohertz, but now I am sampling at a much higher rate, can I exploit this to improve circuit properties, right? Can I exploit this to a larger degree than simply saying my anti-alias filtering becomes easy? Okay. It turns out that this is the subject of what is called the oversampling form, the family of A to D converters called oversampling analog to digital converters, right, where we exploit the fact that there is, you are oversampling significantly. Oversampling significantly means that you are sampling at a much higher rate than is necessary, which means that there is a lot of correlation between successive samples of the signal, correct, alright. In other words, if you are watching a movie, it is like watching slow motion, right. There is, or if you are one of those TV soap buffs, it is like kyunki saas bhi kabhi bahu thi, right. You watch today and you watch tomorrow and it looks like the same thing, you understand, right. There is no difference between successive samples, right, which is basically telling you the Nyquist rate is very low. You come back 2 years later and watch and you will know perfectly well what is happening, okay. So, later on in this course we will see how oversampling can be exploited not only to simplify the bandwidth of simplify the requirements of the anti-alias filter, you can also use it to improve performance of the A to D converter. Okay, is that okay? All right. So, of course, now if the signal bandwidth becomes very high, it may become impractical to be able to sample it at an oversampling ratio this large, okay. In which case you have to settle for more modest values of oversampling ratio, and then simply because you are not able to build circuits which can sample this fast, all right. Now, the next thing I wanted to talk about is related to what I just said. Sometimes you want to sample a signal at a very high rate, that could be A because you want to oversample, or B simply because the signal bandwidth is extremely high, right. A case in point being front ends of oscilloscopes. Today, to test your high speed circuits, you need an oscilloscope which is much higher in speed, right. Only then you will be able to test something which is high speed to begin with. So, oscilloscope front ends have been a big application area for requiring higher and higher and higher sampling speeds. Unfortunately, device technology is may not be advancing at the rate you require, right. Let us say you want to build a sample and hold which is which samples at say 40 gigahertz because you want to test something, then it may not be possible first of all to be able to build sample and holds which can operate at such high speeds, okay. So, one way around that, what do you think you can do? If one fellow cannot do the job quickly enough, what do you think you will do? You put two guys on the job, you understand. So, it is the same thing here, right. So, you can have many sample and holds which are working at a lower rate and put them together and make it look like a single sample and hold working at a higher rate, okay. So, let us take, this technique is called time interleaving, right, where you have many sample and holds working parallelly at lower speeds, making a single unit which appears as if it is working fast, right. So, now that you say okay, then I do not know how to design a really high speed sample and hold, however, I know how to design a low speed sample and hold. If I put many of these sample and holds together in some fashion, I will be able to hopefully combine the outputs in such a way as to make a sample and hold which looks like a high speed one, right. This seems like a reasonable idea. So, this is the principle of what is called time interleaving, and the basic idea is like this. Let us say we had a signal here something like this and you want to sample it at some rate, however, you are not able to build a sample and hold which samples at that high rate. So, in the simplest case I am going to use two sample and holds, one which samples all the even samples, right, and one which samples the odd ones. All right. So, the circles and the crosses represent outputs coming from different sample and holds. Okay. So, please note that even though the effective sampling rate is Fs, each individual sample and hold is working at the rate, in this particular case, Fs by 2. This can be extended to n sample and holds sampling systems operating in parallel, right. Okay. So, let us try and first analyze this. This also serves as a good way of seeing if we understand this continuous time to discrete time conversion and spectrum and all that properly. So, if I had a continuous time signal, one equivalent way of representing this system mathematically is to say I have two samplers operating at a sampling rate of Fs by 2, which means that they are sampling at 2t, but mathematically I can get the samples if I take this signal, advance it by t, okay, and sample it at 2t. So, both these sample and holds or these sampling systems, these switches are being closed simultaneously. It is equivalent to, you can either skew the input signal or you can skew the sampling clocks. Okay, I have chosen simply for mathematical convenience, I have chosen to advance one of the signals. It does, I mean, have a advanced version of the signal, right. It does not, as long as it is mathematically equivalent, it does not matter. Okay. So, now here I have a discrete time signal, which is the samples of the continuous time signal taken at the even instants of time, right. And here what do I have? I have again a discrete time signal where the samples are taken at odd instances of time, correct. Now, how do I reconstruct when I want to use these two signals to make the output look like a sample and hold which was operating at Fs. So, what do you think I should do to these two output discrete time signals? Oh, no, please, if you simply add these two signals, what will happen? You need to stitch. I mean, what is the rate of these samples? Fs by 2. If I simply add the two sequences, what will the rate be? It will still be Fs by 2, correct, but I need to eventually get to a rate of Fs. So, what do you think I should do? What is multi? I mean, if I
select one during one time period and during the second select the next second signal.
Upsample.
see these samples are
For
Upsample.
Yeah, delay.
for
okay.
first for 1t select one first, from
I mean,
t to 2t select the
No,
second.
see, once you have sampled, you only have a list of samples, correct. There is no more time. It's only sequence of of numbers. How will you generate the right? Yes, come.
Interpolated, one signal interpolated.
Correct. I mean, I understand what you are saying, right? But what technically needs to be done is you must first insert, you must
Zeros.
increase the sampling rates of individual streams. That means you must
inside zeros.
upsample each of these sequences So, now upsampling means you insert zeros, every you upsample by a factor of 2. So, you insert zeros, and then what should you do? You must put a delay here, right, and now what should you do? You simply add these two, right. So, now if I put all of this in a big box, this should look exactly like a sample and hold
with Fs.
operating at Fs. Okay. So, obviously, the first question that would come to you is, apart from sheer masochism, why would you want to do this, right? And the answer is that the sampling operation, which I claim to be difficult to implement, is now happening at half the rate. Okay. And so, let us try and figure out the spectra at various places in the signal chain. Right. It is also a good exercise to do, to see if we understand. I mean, we already know the final answer. We know what the spectrum must be at h. Let us remind ourselves of that. So, x d of e to the j omega at h must be 1 by t. It looks, mind you, like a sample and hold which is running at Fs. So, it must look like 1 over t sigma k x c of, what do we see just now, Fs by 2 pi times omega minus 2 pi k. This is what we must get at h. All right. So, the spectrum at A is simply, the signal at A discrete time or continuous time? Continuous time. So, this is x c of f, right. At B, how does the signal look like? Please note that the signal at B is sampled at Fs by 2. So, all we need to do is replace t with 2t. So, is that at B, is it a discrete time signal or a continuous time signal? After sampling B, after sampling it is discrete, correct. So, this is nothing but sigma k x c of, what should I do now? Fs by 4 pi times omega minus 2 pi k which I will write as Fs by 2 pi and pi times k. Actually, I think I made a mistake. Yeah, I think it's okay. All right. Now, what is the spectrum at C? C, mind you, is this signal here. What do you think that is? It's upsampled. So, you are inserting zeros. So, what is it simply
scaling
scaling of the
Axis.
frequency axis. So what should I do? I replace
Omega by
1 by 2t.
Fs by 2 pi. I must replace
omega by 2.
no
It should be
omega with
2 omega.
2 omega.
Upscale.
Correct? You understand? Is that clear? So what must this become?
That is omega.
Omega minus
Pi.
pi. Correct? Now what about the spectrum at D? D is this signal here. Is it continuous time or discrete time?
Continuous.
It's continuous time. So what is the spectrum at D? It's x of f e to the xc of f e to the minus, sorry, e to the j 2 pi f times t. Because it's advancing, it is plus t. Correct? Now what is the spectrum at E? E is nothing but the sampled version of the continuous time spectrum. So it must be of the form 1 by 2t sum over all k xc of fs by 2 pi times omega by 2 minus pi k times e to the j 2 pi, and what should we do? I mean, how do we get the discrete time expression? You form the term f minus k times fs and replace f with please note that you must replace 2 pi f t with, I am sorry, here the sampling rate is 2t, correct, and therefore the sampling rate period is 2t. So, the sampling rate is 1 by sampling rate is fs by 2. Okay. I am sorry, the delay is still, sorry, the delay is t, correct, and I have f, and how do I, what must I do here? I must replace 2 pi f times 2t with omega, correct. So, how does this look like? F must be replaced with omega by 2 pi times fs by 2. Does it make sense? Is the same expressions I am manipulating them with fs by 2 rather than right, and which simplifies to recalling that fs times t is 1, we simply see that this expression is omega by 2, the first term, minus k pi. Right. So, that is the spectrum at E. What would be the spectrum at F? At F it is simply 1 over 2 t sigma k x c of f s by 2 pi times omega minus pi k times e to the j omega minus k pi. Right. Now, what are we doing? We are delaying this by one sample, correct. So, this is what, how does that look like? G is simply the stuff at F e to the minus j omega. So, what goes away? The plus j omega and the minus j omega go away. That makes intuitive sense, because we have advanced the signal here by a factor t, and we are delaying it by one sample, which is also, I mean in time it is time t. I mean the at C and F, what is the sampling rate?
Fs. Fs.
It is at Fs, correct. So, that goes away. So, this simply becomes e to the minus j k pi times pi. And what are we doing finally? We are adding the stuff at C with the stuff at F. So, let me just copy and paste this is what we had for things at C, all right. So, now if we add, I mean what is so funny about e to the minus j k pi? It is, yeah, it is minus 1 to the power n. So, for even values of k it is 1, for odd values of k it is minus 1, all right. So, for k equal to 0, how does this look? One by t x c of f s by 2 pi times omega, correct. For k equal to 1, what happens? For k equal to 2, I am sorry, k equal to 1, this argument is the same as this argument, correct. This is 1, whereas this is minus 1. So, when you add the 2 go away and you get 0. So, going in the same way for all odd k, these things simply vanish, you understand. So, this is only valid for, these things will be non-zero only for, so at h it will be of the form 1 by t times sigma over all k, all even k, which I can simply say as f s by 2 pi times omega minus 2 pi k right. You understand, which is the same as what you get for a sample and hold operating at the full rate. Okay. Well, this is where the math stops from the communication point of view or the signal processing point of view. When you make a practical system like this, there are a whole bunch of problems, right. For instance, there might be an offset here, right, which may not be there in that path. In other words, there is a DC offset which is different in both paths, all right. The next thing is that the gains of both the paths may not be exactly the same. The third thing is that you want to, in practice you are not going to implement it like this, you are going to, one switch is going to be sampling at 2t, 4t and so on, the other switch is going to be sampling at 1t, 3t, 5t and so on. But in practice what happens is there are two independent switches, so the exact sampling instance of both these switches may not be exactly t apart. So, you ideally want the first sample and hold to sample, the second sample and hold must exactly sample a time t later. In other words, both of these are sampling at a sampling rate of fs by 2, that is every 2t, but the offset between their sampling instants must be exactly t, right. Otherwise it will be like, if there is a small skew, then it will be like one is sampling here, the other one is sampling here, this guy is sampling again here, the other one is sampling here and so on, you understand. So, this corresponds to some kind of non-uniform sampling of the input. All these will cause artifacts in the discrete time spectrum which must be addressed, you understand. So, we will continue with the effect of these artifacts, which are fundamental things which will happen every time you implement a time interleaved sampling system. We will see this in the next class.